hacking serverless runtimes, profiling Lambda, Azure, and more. If this is not the talk you intended to see, please leave. I'm Andrew Krug. I'm a security engineer for Mozilla. I primarily do cloud security and identity and access management, and I am presenting today from Firefox Nightly, the best browser in the world. I also started an open source project here at Black Hat last year called Threat Response that is doing an Arsenal talk tomorrow. So if you want to come and see me talk about less red or less purple things, don't miss that. I'm in the main theater over there.
And my name's Graham Jones. I'm a software developer up at LegitScript in Portland. And I mostly do data warehousing and analytics. And also I've got some background in Lambda, which we use for some of our internal applications.
So you may be here wondering, what exactly is a serverless, as a good friend of mine says when he often doesn't know what something is. In a nutshell, serverless is your ability as a developer to write code, hand that to a vendor. There's some sort of sandbox execution environment, and then you basically only have to worry about consuming the net result of that operation. So these runtimes that are at the heart of serverless functions are largely what we would consider to be ephemeral. We hope that the environment kind of goes away at the end of the compute and that all that's left is the output data at the end. So why would you consider using serverless at all over your regular brick and mortar systems and your data center or EC2? The advantages are pretty broad. The first and foremost of which is parallelism, just basically infinite scale-out-ish. One of the more compelling features. Doing patterns like fan-out pattern is easy, but there's some other tangibles like automatic event-based triggers for other things that might happen in the cloud. There's a number of great security features, HA by default, enforced architecture, and little to no management. So if you're a startup or you're a big company, you get to collapse all your operations, in theory. So another way that I like to put that is that serverless compute is hope, right? We hope so many things about serverless. And don't get me wrong, I love serverless compute. I use it for a ton of stuff in my day job. But as a consumer of this, I have all these hopes. I hope that my code executes securely. I hope that other people can't tamper with the execution of that code. I hope that the vendor is patching the operating system running those environments. And I hope that that code hasn't been somehow modified in transit to the sandbox. Bottom line, I hope that this is somehow more secure than actually running my own servers. Because I'm pretty good at running my own servers, right? I hope. What will you learn in this talk today, the 3 takeaways that Black Hat asks us to give to you? Hopefully you will take away how different vendors implement their sandbox. At a very high level, we're going to talk about the isolation technology or lack thereof. We're going to talk about attack patterns and techniques for light persistence in these environments. And we're going to talk about how to build your own test tools to hack the sandbox. How do you do a little bit of digging around and figure out how these things really work on the inside? This is the quote-unquote hacking part, hacker spirit of this talk. I also like it. I would like you to take away whether you should embrace this technology or avoid it altogether as a consumer, as like kind of the bottom line. What you won't learn in this talk, I love it when people do this, you won't learn kernel-level exploits, because I didn't make any of those. If I did, I'd probably be rich, and not talking at Black Hat. Container escaped, the hypervisor. I won't do this. If I had a hypervisor escape, again, I'd own an island or something. You're going to see some Python in this talk. That's important. I love Python. You're going to also see some Node.js. I love that less. And you're going to see some IAM policy docs. A quick favor, though. Most of the things that I'm going to talk about are related to some initial vulnerability that was introduced either through misconfiguration or a little piece of bad code. And we really want to look at when somebody kind of like gives you that foothold in the door, what happens next and how bad does that get in different vendors' environments. Because bad code is bad code. It doesn't mean it's necessarily the vendor's fault. It's just that we want to know what the pivoting potential is and lateral movement potential. With memes like this cycling around the internet, we all know that bad code does make it into production, and it makes all our lives hard, which is why we're here. So this is where serverless can be dangerous, right, in some sets of circumstances. I love that one. So who even sells this serverless thing? Almost everybody. Amazon was kind of the first player to bring it to market, but GCP, Microsoft Azure, they have offerings in the space. There's a great open project in IBM Bluemix called OpenWhisk that I have great hope for. And we looked at a little sandbox as well called Auth0 Webtask. So what do people even use a serverless thing for? It's relatively new, probably nothing critical, right? So the answer is that we have this whole smorgasbord of apps, and they really range from low-risk to high-risk apps. You have people using serverless for chatbots, and on the more high-risk end, you have them using them for identity providers and things at the very heart of our infrastructure. So it's really anything and everything. My boss sent me this tweet while I was making this slide deck that apparently somebody has made an engine even that you can use to run Docker containers inside of Amazon Lambda functions. This was my reaction. Why would you want to do this? It seems like a really great way to totally give away every feature that's afforded to you from a security perspective by Lambda, right? So let's just count the layers of abstraction there. It's a container running in a sandbox container, running in a virtual machine on a compute host in the cloud. Let's count them. That's 1, 2, 3, 4, 5, 6 layers of abstraction between you and the thing you actually have to protect. That is so different from when I first started this, when I had a fleet of NetWare servers that looked like that. Sometimes they turned off and on again. It was great. The point is, though, that people will really do anything and everything with technology if they can. If they want to do it, they'll find a way, and so we need to learn more.
So for these sandbox providers, now we're going to talk about what are some of the attack surfaces that we're going to cover in this talk. And the main systems that we're going to cover is at code, so when the code is at rest, and at the execution time of that code. So this first one, at code, this can be if you have access to the GitHub repo, you gain some other sort of source access, or it could be something like a subdomain takeover that lets you hijack the deployment pipeline, just some point at which you can change the actual code before it even gets deployed. Now, if you have this level of access, the second step is probably not as important to you because you don't need to worry about an exploit. You can just put whatever you want right in there. But we'll come back to this, so keep this one in the back of your head. The second method, and the one that we're going to talk about most, is exploits that are at the runtime or at the execution. These are all sorts of classic things. Things like SQL injection, getting able to run arbitrary code, or string concatenation exploits. And then once this happens, within the runtime, what are some of the pivots that you're able to do based on the permissions of that serverless function? So now you're saying, so what, right? We've all heard of these attack types, but the difference is that the pivoting potentials from these within your serverless system architecture can be different than what it was on your traditional server. And we're primarily concerned with persistence and data exfiltration, because these things are really different in the serverless architecture. So to do this, we're going to come back to some of those things that Andrew touched on about what we believe is true about serverless. First, sandboxes should be thrown away at the end of execution. And this comes back to, ideally, if this happened every time, it'd make persistence really hard, because there would be no persistence from execution to execution. This is not always true, and we're going to go into some of the ways that sandboxes not being thrown away can lead to further exploits. Secondarily, sandboxes should have minimum execution times. And although you can set these yourself down to whatever default you feel is reasonable, if you don't set these correctly, your sandbox, if it starts running someone else's code, can run far over, up to perhaps even 5 minutes, which is the default in some of the cloud providers. And 5 minutes, it turns out, when someone else's code is running on your system for 5 minutes, you can do a lot in 5 minutes. So we're going to cover a couple pieces of terminology for those of you who are less familiar with serverless. Let us touch on persistence. So the first term is a cold start. And this is after I've set up my serverless function and I call it for the first time. This is loading all the code off disk, instantiating the container, setting the environment up, loading any background code that only gets loaded once, all those startup costs that have to go the first time. And there is a performance penalty that's paid for this. So this is a cold start as opposed to a warm start. So to get around these performance issues, most serverless providers allow a function that has recently been called, when called again, to reuse much of that initial infrastructure. Potentially, you could wind up with the same container, There could be code in your runtime that's still loaded, and there could even be files on your RAM disk that are still there from an entirely previous execution, which opens the door for many of the persistence attacks.
So the first person to discuss these type of attacks was Rich Jones. He's also the creator of a serverless framework called the Zappa framework. He presented at CCC last winter this talk called Gone in 60 Milliseconds. We cannot dive as deep as he did into AWS, but if you want to go and see kind of in a worst case scenario, if you blow IAM permissions a little more open than the defaults, what can theoretically happen, this is a really great talk. So these environments have outer and inner attack surfaces, right? So they have ideally the hardened outside and the chocolatey center, so to speak. And the outside is API gateway. In Amazon, Azure functions and other vendors have similar analogs to that, where it's a mapping of REST methods to serverless execution. So that inner surface is really, in the AWS case, the Lambda function, or in Azure's case, the web function, and that's where our code actually executes. And if there's some human error or a lack of skills in auditing IAM, that's where you have these potential pivots to other services, because you do have the same lateral movement ability that you have inside of any cloud. So if you're scanning for this from the outside, there are some indicators that you might be hitting serverless functions. And I'm borrowing a little bit from Rich here. This is directly from his talk, almost. There are some headers that Amazon sends out, like CloudFront cache headers and things that aren't a smoking gun, really, that you are talking to a Lambda function, but they're a good indicator that you might be. In the case of WebTask actually is that right out in the open. You definitely know that it's WebTask. And Azure just says it's IIS because it's Microsoft, and everything is just IIS probably somewhere. So you really don't know that that's an Azure function from the header. You can also just search GitHub, like anything, really. And there's a lot of frameworks that are becoming increasingly popular. The aptly named Serverless framework has a config file called serverless.yml, and you can see it has a very high number of hits, over 13,000. So we have serverless apps located. What do we do with them now? In order to attack these environments, we really have to understand what's possible inside the containers themselves. So our starting point, like any good attackers, was to go to the vendor's documentation. And this is what we found. Nobody really writes about how they construct these things. The most transparent vendor is Auth0. They actually have an open reference guide, but nobody's really good about saying how they build security and allocation around these environments inside of their cloud, largely because it's probably proprietary, trade secret kind of information, but it's just not super public. And if it is, it's very obscure. So I'll ask you if you have a problem with using a tech stack that you can't audit really how it works on the inside. So we did a lot of digging around. We were inspired by this project by a researcher by the name of Eric Hammond. He wrote a tool called Lambda several years ago that was more of a web shell wrapper that just ran OS-level shell-out commands to kind of dig around in Lambda runtime. He published some of the very, very early work around figuring out what goes on inside of a Lambda function. So we did like some very similar stuff, and we evolved that until we had 14 or so core tests that we would do with these OS shell-out commands to figure out what hardware was it running, what was the kernel, what Python packages were available, et cetera, where could we write? And we'll talk more about this towards the end. But we have this great, big, rich profile now of information on these environments. And we looked for common things, like is this an operating system, or is this something totally proprietary that just implements a custom version of the language runtime? Can we read and write everywhere? Can we poison the code once it's in the environment? Can we get and set environment variables? Are the cloud permissions too permissive, too tight, or just right? What about internet access? Do I have egress versus egress and ingress? Can I pop a shell on these things? What even are they? So this is a little bit like playing Operation, right? Because you want to do this without the cloud provider revoking access to your account. So we definitely got in touch with all the cloud providers and joined their bug bounty programs and all that good stuff, so we didn't touch the sides. But if you're going to do this, do notify providers. We explored Lambda, Azure Functions, and Auth0 WebTask, like I mentioned. So 2 big box vendors, 1 small, very purpose-built sandbox. So let's talk about Lambda first. Lambda was kind of first to market with this. It's been around a while, so we know quite a bit about it from work that other people have done. We know it's some kind of containers. Nobody says it's necessarily Docker, but we know it's containers, at least. That it runs on a Red Hat 6 derivative, Amazon Linux. It's a read-only file system. Code gets injected into /var run task. It runs as a non-root user. All great things. Single IAM role accessible to the sandbox in terms of pivoting in the cloud. Reverse shell's probably not possible. At least nobody's done it yet that I've seen. And we do have internet egress, and I put in parens in some cases because you can deploy these without any access to the internet. So we wanted to know if we can steal credentials from these environments. And when we do, how bad is it? Where can we persist code if we do manage to get remote code execution? How long can we do that for? Is it really persistence, or is it like ephemeral persistence? Can we get Lambda to do things other than execute code in the language that we prefer to use? So if I say I am running Java, can I execute Node or Python or Perl? And how frequently does the OS and runtime get patched? Python modules, Node modules, etc. So I have some sample output here that I'll show you from our profiler. This is more just to illustrate for your brain what the output is. So it's JSON structure of all of these checks. You can run this in your own environment. We'll open source the code for this at the end of the day. But you can see we really collect quite a lot of information about each runtime, and we log and store that. So from this profile, we know that Lambda's container structure looks a lot like this. It's got API gateway, which has an event trigger, to a copy of the code that gets loaded into the container on that cold start from the bootstrap. And from there, pretty much everything in the file system's read-only except for /temp, which is mapped to a RAM disk. And /temp is going to be different size depending on how much memory you've allocated to your Lambda function. In addition to that, you have a few credentials. You have basically session token style credentials for the IAM role. Nothing super groundbreaking there. So what's your strategy given these limits? You have very, very small attack surface, right? So as a malware author or a pen tester, you can kind of be laser focused on how you're going to attack this environment because you can really only attack it one way, right? Your initial payload probably needs to be as small as possible because it needs to pass API gateway. You need to persist in /temp, which could be very small. And then you need to assess lateral movement very fast and exfil your results to somewhere else. In other words, your attack needs to be bigger on the inside. There's some Doctor Who fans in the audience. Python minification helps with this. So there's a great project called PyMinifier that you can use to take any set of Python code, and I like to write most things in Python, and you can shrink it down and even compress it so that it's this really tiny, pastable blob. So I wrote some reconnaissance code that I used in some of the research that I did, which is linked to in our white paper, where we just try and figure out what can we do in the IAM role that we're in. Can we create cloud watch log groups? Can we attach ENIs? Can we do A, B, and C in the Amazon environment? So really it's kind of like brooding out permissions by simply attempting Bodo calls and then returning exceptions if we can't. So what that looks like, if you take a bunch of them and you minify them, is this. So there's another great script called one-linerizer that will turn anything into Python one-liner, which is also super great for making malware for serverless environments because you can just squash it down in the most complex set of Python lambdas that you've ever seen. So we decided it would be a great idea to take these techniques and then create for you some demo apps that have some vulnerabilities in them so you can really see what an attack like this looks like from both the IR perspective and the red team perspective. So I built a Slack bot, built-in serverless framework for Lambda. It takes a GitHub webhook on commit. It notifies the Slack channel that there was a commit, and it has a code injection in it through a basic string escape. So the normal behavior of it looks something like this. The bad behavior looks something like this. And I have a little video demo. I'm not going to do it live because you would be waiting forever for me to paste all the tokens I need out of Slack. But I promise I recorded this right before this talk, so it totally works right now. So you can escalate out of that. And you'll see that in the video, and I'll kind of speak to it here in just a second. So the attack surface, though, notably becomes very large with bad IAM permissions. And the issue is here in Lambda are not Lambda's defaults, because Lambda's defaults are very good. The issues here are the defaults that are being introduced by popular serverless frameworks. A lot of these frameworks are brand new and they're just coming to maturity, and they tend to blow the IAM permissions wide open to start. And there's a footnote somewhere in a guide that says, go back and harden this yourself, because we don't do IAM permissions super well yet. So this is a snippet out of the default IAM policy for Zappa. You see it has a lot of stars in there, which if you do AWS stuff, you know is bad because you can interact with a ton of resources. So the IAM struggle here is very, very real. My boss likes to say IAM is the killer feature and the killer feature. So detection can also be hard here. So we have a lot of mature stuff for detecting attacks like this on-prem. We don't necessarily have as many of the same kind of facilities in the cloud with regard to serverless. You really only have CloudWatch logs. So one of the pieces of advice that the AWS security team likes to give out is don't leave your DeLorean in the garage if you want to go back in time. So if you're authoring these apps, build mature log pipelines into them, because that's really the only way you're going to get anomaly detection, and CloudWatch logs in the case of AWS is that. So I have this bad Slack bot demo, which I'll just go ahead and kick off here. And so we're just having a casual chat here in the threat response Slack channel. And I'm working on an ostensible feature for a feature that I call bad repo that creates this initial webhook out that notifies Slack that there's been a commit. And people are lazy, so you can ask it for change logs, you can ask it for README files, and it'll just return those to the Slack channel, so you don't have to go to GitHub to look at those. And so there's a code injection here in where you put the file name, where if you just stick a semicolon in there because of a string concatenation vulnerability, you can get arbitrary code injection into this container, and it will return you the output. So here it is returning the actual changelog, which I put in Star Wars ASCII content, for amusement. And that's going to go round and round in there for a little while. I'm just validating here that the changelog is actually as it's supposed to be. So this is normal behavior for the app. There's the Star Wars ASCII text. There's the vulnerability itself. It's an os.p open instead of a Python file read, which we all know is bad, but somehow they still make it in sometimes. Code reviews are important. So there it is, nice and large, awesome sauce, string escape. So now we come in here and we replace our changelog with just an ls to make sure everything's working. Great, I get back like ls output. So I can do more cool stuff now, right? I can do ID. Am I running as root? No, I'm running in Lambda, which runs as SBX user. Super cool, great. So now I'm going to get the environment back, which contains all the juicy stuff in terms of session tokens, security tokens, and stuff. Before you get super excited, these are already dead. Here they are in my Boto profile. And so now that I have it in my Boto profile, I'm interested. Can I do S3 stuff? Not with this profile. So, because this is the default Amazon Lambda sandbox. So who am I? Get caller identity. And you can see it returns that it's the poor webhook Lambda role. So there's a great script in the AWS Pwn repository that'll just go through and it'll brood out what you can do in Amazon using describe statements. And this is like one of the only ways to figure out what permissions you have from the outside as an attacker. The downside is this super, super noisy, right? And it takes kind of a long time to run. But I managed to make it through a whole run with this session token. Again, this particular role that I'm working with is super locked down, but this is where all the goodies would be. And so the last thing I'm going to do before I go and try something else is I'm going to run get session token to see if I can shred more tokens so I can keep not working in Lambda for longer. And the answer is no. So now I'm going to try running another arbitrary Python command, because if I have one Python process, why not have two? And apparently I can. So that's also awesome and interesting. And so we know from our profile output that Lambda has Boto by default, so we can really do any exploration of the AWS account that we want using Boto calls. And this is where that one-line Python stuff really comes into play. You see here I ran get caller identity inside the sandbox using only a one-line Boto call. So you can explore inside and outside the Lambda sandbox using these one-liners. So what does that look like from an IR Defender perspective? It looks really, really weird, right? So if we look at the CloudWatch logs, there's some things in here that you will see that are totally stand out as far as this is non-normal behavior. It's about as non-normal as this, right? We have anomalous execution times, high error rates, CloudTrail high denials for the Lambda role. So it's as detectable as this moon balloon from last year. CloudTrail also outputs denials. A lot of people don't actually know this about CloudTrail, that it logs successes and denies. And you can actually consume those denies in a CloudWatch event pipeline, and you can programmatically take access on those. So kind of the TLDR here is that it's only really as bad as the IAM policy that's attached to the function. And you can auto-IR this. So your mean time to respond is about 7 to 10 minutes, because you can only IR it when the CloudTrail log rolls over to CloudWatch events. But 7 to 10 minutes is still probably better than a human. So now Graham's going to dive into Azure functions.
So when Andrew and I started looking into these, we were both very much familiar with the AWS ecosystem and not as much with the Azure ecosystem. And as that may be the case for many of you, a lot of what we wanted to dig into here was the differences in the Azure ecosystem and how the permission models are different. So for Azure, shockingly, it runs on Windows. And then the big difference is that it has sets of functions grouped within apps. And so unlike Lambda, where a function is basically just a little container that gets spun up and then spun down, an app is basically a whole deployed Windows server somewhere that's going to be running IIS and has all your functions sitting on the file system. This file system is largely writable. It does have internet egress. It doesn't have a root user. And then, like I said earlier, all the functions within the app do share the same system and the same permissions. The app root is on the D drive and D home. The C drive, where all the system components live, is immutable, but the D is writable. And then the code is injected into D site, www.root, and then the function name. And we also have some secrets stored on the drive that we'll get to later. And they are encrypted, but with some shared keys. So the reason that you would group functions within an app, before I go into the problems with that, is that in terms of a metrics or resource management perspective, an app is one group of resources. So if you want to manage a set of things as one group, a lot of times it can make sense from that perspective to put it in an app. So we wanted to know the same general questions as Lambda, but instead of pivots through IAM, we wanted to know what one function can do to another that are within the same app. And so before we dive into that, just a couple other tidbits. We didn't have WMI access. And if you call getEventLog list, you can see the list of logs, but it's very tantalizing because you can't actually get any of the events. So it is moderately locked down from these functions. For digging around, we started with the same profiler system, but many of the same profiler components didn't work because they were POSIX specific. Fortunately, because it's a less ephemeral system, there's actually just this Windows machine running. It means that it's easier to work with for digging around. You don't have to go in and script all these Python shell calls. There's a Project Kudu UI that actually gives you command access. You can also use PowerShell for anyone who's a PowerShell fan. And you can just wander around the system, poke around, see what you can write to, see what you can't. And it did make investigating around initially much easier. So for the vulnerable app here, I'm going to show you what's really possible if you manage to break open one function within an app and what it can do for the other function. So the concept is going to be that we have a credit card batcher, the idea being that you use your credit card multiple times, it sums it up, and then it bills you once at the end of the month to save on credit card charges. All these functions for this whole app ecosystem are going to be in one application. So the exploit that we're going to use is it's all in Node, and so we pass some JSON to it that gets evaled. And we're going to use the fact that in Node, you get past a context object originally with a callback to say when you're done because of the Node callback structure. What happens instead in this arbitrary code execution is that you can trigger that done early and thus return whatever data you want and not have to worry about exfiltrating your data all the way through the rest of the control flow of the program. This is an indicator of compromise in the logging, though. Logs are still important. As you can see that you have this error here where done has already been called. And this means that you called done as part of your exploit. The program kept running in the background, and then it reached its intended end and called done again. So this is a sign that something's wrong with your control flow, whether by your doing or maybe someone else is doing. So this is the basic layout of the application. First, we're going to show the intended use of the API. Then we're going to demonstrate how the vulnerability of one function, we can change the API keys for other functions, giving us access to them. We can change the ways that other functions are triggered, bringing functions that were not previously accessible via API to then being able to be called through API endpoints. And we can even change the source code of other functions within the same app. So I have a series of Schema demos here. So this first one is just going to be the basic use of the app. So it's going to be through curl, basically in everything. I'm going to have a JSON file, which is going to be the code, the contents of my post. I have a config file, which is just there so that we don't spam up with the URL and my API key, and has some headers. So you can see with this initial one, I do my curl, I send in the right data, I use my credentials, and then I get back the charges that I've made on my credit card. Pretty straightforward. For the second piece, I'm going to show how with this print return JSON, so this is not some JSON, but this is actually JavaScript that then gets evaluated. So this is a pretty contrived vulnerability, but sometimes the node runtime has vulnerabilities. That just happened recently. There's a talk on JSON parser vulnerabilities here. Could be all sorts of things. So with this arbitrary JavaScript that we have at the beginning, you can see we're able to populate the context object with whatever we want to return and call context done. And then the rest of the program just gets ignored, and we get our custom text returned here. And then this is also going to be generating one of those warning log statements that I touched on earlier. So after that, we've shown that our vulnerability works. We can proceed to list functions. And list functions is a very similar thing. It turns out that these files here are all metadata for the functions, showing how they're going to be called, what some other attributes are. And so we're basically just doing an ls on the file system. And we can see all sorts of things here. So public vuln here is what we're calling into. But there are some other things that might be interesting. Total view probably has a lot of information that's interesting. And then billing sounds promising. So we'll get to that eventually. We'll try total no auth first. So we do our curl, send in no data, and we try to hit that endpoint, and we get nothing back. This is empty. This is because total no auth uses a different API key, because even within the same app, you can set different API keys required for each function. However, that doesn't need to stop us, because these keys are all stored encrypted on disk, but they're all encrypted against the same key from function to function. So I can actually, in this snippet of JavaScript, just take my key and copy it, the key that I have for the function I've already accessed, and copy it over the file for the one that we don't have access to. So we call this curl. That works successfully. And then using the exact same curl statement as before, I'm able to call it, and then I see all these card IDs for everyone. I now have access to this function. So that's great, getting to see all sorts of things. But now we want to get at some stuff that really wasn't accessible via the API at all, not for anyone. So we're going to see how we go about digging into billing. So the billing info here, at this first snippet, you can see we're just reading the file, this function.json file, which is similar to what we listed earlier when we said what are the list of functions within this application. And for those of you who are familiar with cron, you can see that this JSON contains a cron line. Here's our monthly schedule. And so it's a monthly billing function. It'll just run at the beginning of every month, which is pretty reasonable. It's like what we'd expect. But since we want to change billing, and we don't want to wait till the end of the month to see if our exploit worked or see if they've deployed since or any number of things that could happen, we want to change it to be able to be called through the API. And so, just like we could change the permissions, we can actually, with this next snippet, take our configuration file for our vulnerable endpoint that we're writing to that says, hook this up to the HTTP endpoint, take post requests, so on and so forth, and just copy that over the billing, thus changing the billing from being activated by a cron monthly to being activated whenever we decide to hit the API endpoint. So you can see in this next snippet, we change the billing to be an API endpoint. Then we do the same operation we did earlier, where we give it our known API key. And then you can see we can post a billing. And so this gives us the summed up prices for our card. Will be billed $30.98, and then someone else's card. So that's great. Now we know how much we're going to be billed, but we don't really want to be billed at all. And so we can even look at the source of other files. We can start by just traversing the file system, going into that directory, and dumping that source out. And so at this point, not only can we go on to our next exploit, but also you can see that in here there are some database credentials that they didn't use an environment for. There's a server endpoint that wasn't parameterized out. All sorts of juicy things that are in source code that you might think was never intended to be publicly accessed. So after we see the source, we can find the portion in it where the charges are summed up, and then actually, with this next snippet, we're just going to do a regex replace and say, go through this file whenever we sum up all the credit card numbers. Instead, take our charge, our number, and just set it to 1. And so we have full access to the file system. We can just write this file in. So we curl this in to patch the billing code. And that's done. And then you can see when we call the billing code again, we only have $1 on our credit card. So just the vulnerability in this one function let us change the source code, the access type, and the access key of all the other functions within this app. So having separate API keys is great, but it clearly didn't prevent this kind of scenario. You need to be aware that if someone does gain access to one function within your application, you have access to all of the functions, essentially. And be aware of the choices that you're making by putting these functions within the same application. Next, we're going to talk on Webtask, who provides Auth0, the smallest provider that we covered. Webtask is open source. We love open source. This is great. They've even got their GitHub here. They run Docker containers on CoreOS. They allegedly run Node.js only, which is unlike many of the other providers where you have Python or PowerShell or Java or all sorts of other things. They have no restriction on egress. And people use them for all sorts of things, including the Auth0 rule engine. And you can have a public tenant out in the cloud, or, depending on your plan with them, you can have a private tenancy too. So there are different options for how this can be hosted. So at first, when we discovered this, we thought, well, it's Node.js only. All our profiler is written in Python. We don't want to have to do the whole thing again. So we were sad. Right? It was sad. But we dug around a little, and we found that by requiring child process and calling exec, you can basically shell out and run shell commands. So a friend of ours wrote this cool little web shell, which might be hard to see, but basically it just lets you put in arbitrary commands. You can see here's an ls, and you get the output of the ls. You get some file system dumps right here. So this is great for us, because we didn't have to write any Node.js anymore. Because if you shell out and call Python, you can see that Python 279 is also on those boxes. So we got to explore around a little, run our profiler, and we even found some other cool stuff like backchannel.sock, which we'll touch on a little later. So we have this forked process demo, which is going to be live and it's worked 2 times out of 3. So basically, what we're going to do is we're going to open this first link, and this is going to have, so we're running Python. We shelled out and just called Python with no arguments. So it's waiting for input from standard in, and this is running now. And what we're going to demonstrate is by opening up another link and running PSAUX, we can actually demonstrate that we hit the same container, and you can see here our Python is running. So with these two entirely separate ephemeral containers, we're actually hitting the same container and have overlap between the functionality. So in Auth0, we learned that forked processes do hang the container, which is what's allowing us to do this demonstration and hit the same container multiple times. Backchannel.sock is not anything too crazy. It's a socket that hits a REST endpoint, which is probably for credential exchanges. You can escape the sandbox to the container, as demonstrated by all our ability to call Python or shell commands or whatever else is on that Linux installation. And the sandbox system is Debian-based with a little anomaly detection and some extra monitoring thrown in.
So the last thing that I want to talk about is something that's not quite done. So we have 3 things to give you today, 2 things that are open source available at the end of this talk, the first of which is the serverless profiling engine that we wrote to do this. It works in any POSIX environment. Those vulnerable apps are going to be available today, so if you want to take those home and deploy those in Azure or AWS and poke at them, you totally can for anomaly detection. The serverless sandbox profiler, serverless showdown, does everything that our profiler does. It just gathers that for you in the form of an API that collects that data in Dynamo database and then allows you to score that on a security scorecard using a rule engine. So this is really important because it allows us as consumers to take any vendor and stick a little bit of code in their code sandbox and let it tell you when the environment changes. Let it tell you how often they patch it. And it really allows us to keep the vendors honest about what's going on inside these sandboxes. And so this is an example of what a scorecard would look like. At Mozilla, we love observatories. We have the TLS Observatory Web Observatory. And so I made this in the spirit of that. I'm calling it Serverless Observatory. The code for it is available today, and it will be available later this year as a SaaS offering, totally free. You can sign up for it on our mailing list at threatresponse.cloud. This is the final slide that really tells this story about how all these security features stack up. You can see that a lot of the vendors have really similar security features. None of them restrict language that's executing. Most of them do have read-only file systems to some degree in some places. All of them patch frequently. None of them have immutable environment variables, etc. You can read more about this in the white paper. If we could ask the vendors for something, what would it be out of all this? What would we ask the vendor space? We would ask them for any control that requires out-of-sandbox levels of access, right? So we can all think of some additional controls that we might like. So we might like the ability to do native code signing and code signing validation. I want something killed if it's not end-to-end signed, right? I want immutable environment vars or a config store that guarantees immutability. I want the ability to choose cold start in favor of security instead of performance. I want the ability to kill any process that's not in the language the runtime specifies. Wouldn't that be cool? And I want more transparency in the patch cycle and the so-called trade secrets, because we all know that transparency is almost always better for security. So should you use serverless? Probably. It's still probably better than most of the stuff that people will do on-premise, but really you have to put that against the risk profiles for your application. The security advantages are actually quite good, and there's not that much attack surface there. Event-driven security gives you a lot of additional anomaly detection and auto-IR capability, specifically with some of these facilities in Amazon that I absolutely love. And I'll leave you with one quote, and then I'll take questions. And this quote I stole from a Microsoft presentation. Modern security does not resemble high walls or strong doors, but rather bells on strings that ring each time an attacker moves forward. And I think that's a really great quote that represents modern OPSEC. So thanks to all these people who contribute to our awesome project. Last year we had 4 contributors, and now we have 16, so that's our shout out to those folks. Thanks to the vendors for being super awesome in working with us and giving us access to the teams without a pile of paperwork. And I'll take questions now. Any questions? Lovely. Thanks for coming.
I have a question.
There is a question.
Yeah. Is this on?
Yeah.
It is on.
Did you do any work with pre-compiled code in Azure Functions? This was all script.
We didn't do anything that wasn't Python or PowerShell. We had hopes to do C# at the outset of the project, but our expert C# developer dropped off.
Oh, okay.
We'd still like to.
We did also do that in Lambda. We showed that you could upload a binary, persist that in temp, and then call that from your interpreter.
Were you able to write to host JSON or function JSON in?
Yes.
You were. So arbitrary code execution at that point.
Yes.
Oh, thanks.
Yeah, we're also available after this if anybody wants to chat.
Quick one. When you were talking about visibility with Lambda, it occurred to me, I don't know if this is possible, but I wonder if you looked. My understanding is that Lambda functions run in a VPC by default, and I'm wondering if you can enable net flows within that VPC to get more visibility into what's happening.
So the question was, can you get VPC flow logs from the default VPC that Lambda functions are associated with? The answer is no for the default one that only allows internet egress, but if you do custom VPC and you deploy an internet gateway, yes, you can get VPC flow logs and you can use your standard anomaly detection bro pipeline.
Have you seen these exploits in the wild, or is this all stuff you've dreamed up in your evil genius laboratory?
I can't really speak to incidents that I work on, but I can tell you that people are exploiting serverless functions in the wild, especially in the open source space where it's really easy to see where the vulnerabilities are in the code. Yeah, it definitely does happen. I don't have any data on how frequently.
Yeah, with all the work, hello, can you hear me? With all the work that you did with AWS to get all the startup, cold starts, warm starts, all the event data, and the lack of data that you would get in transparency from the other vendors, would you be able to give them feedback loops to help strengthen some of the visibility on those?
The question, if I had to summarize, was the net result of the project a better conversation with these vendors about transparency? Yeah. Does that summarize it? Yeah. They're definitely asking us at this point what we as consumers would like them to add to their products. And so we're talking about patch management feeds or risk scores for warmness on several levels right now with all the vendors that we worked with. So
great. Thanks for your work.
Thank you.